All right, how's it going, everybody? Welcome to the beginning of the spring 2021 semester here. I am making this first video here. It's Thursday, January 14th, a little bit before the semester starts. But I'm going to plan on Thursdays and Fridays creating the videos for the following week's content, which is why I'm making this video here a little bit before the first week of class starts here. So today I'll be making a video covering section 6.1. Tomorrow, Friday, I'll be making a video covering section 6.2, so that these are available for you in our first week of class here. So in general, this will be more or less the format of my videos here. Some sections of the textbook will require me to spend some time explaining some concepts. Other sections of the textbook will not. It's always going to be my expectation that you've read the textbook before you watch my videos here. So this should just be sort of like our further explanation and our look at a couple examples here to help you out with the computation that you'll have to do associated with your My Open Math homework and our coming by hand homework assignments. We'll get our first one of in week 2. In general, I'm going to be trying to make our videos here be in the ballpark of, they're going to end up being in the ballpark of like an hour. Sometimes I run a little bit longer. It's definitely my goal to keep these as short as I can make them. I don't want there to be lots of fluff content in the videos. Then again, I sometimes get a little bit long-winded, so I'm sort of always fighting against myself on that one. So I'm going to do my best to be concise when I make these videos here. But as you'll see, I'll sometimes get a little bit carried away here. So we are starting our textbook here, by the way. We should all have our purple algebra and trigonometry textbook by Sullivan here, 7th edition. In this textbook, we're going to be covering chapters 6 through 9. Yeah, 6 through 9 essentially here. And so we're starting in chapter 6. There will be one point in the semester where we're going to dip back for one section into some previous algebra topics because we're going to need to make sure that we have there's a very important algebra concept that'll be coming up in a chapter or so that we're going to need to make sure that we're familiar with. But other than that, we're going to, for the most part, follow through chapters 6 through 9 in essentially the book order. I'll have a couple small tweaks to some things, but we'll be pretty consistent with our route through the book here. Very importantly, section 6.1 and 6.2, they're not necessarily terribly difficult, but they absolutely are like the cornerstone of the entire semester here. In section 6.1, we introduce some basics of measurement associated with angles and circles. In section 6.2, we'll introduce some basics of measurement associated with right triangles. These two things are going to be introducing concepts that we will use literally every single day, every single section of this class for the entire semester. So nothing too terribly difficult in 6.1 or 6.2, but like you can't not know this. This is going to be our cornerstone for the entire semester is our introductory sections here for the start of chapter 6. So let's go ahead and get into that. And I guess before I actually start right here, I will say I certainly expect that there's going to be content that everybody is already slightly familiar with, both in section 6.1 and 6.2. I'm also very confident that there's going to be content in these sections that most people are not familiar with. So it might be the case that you're seeing a few things that you are already familiar with, but this is not... I very rarely experience a student who is already familiar with all of the content in 6.1 and 6.2. So let's kind of make sure that we see all the parts that are here since all this stuff is going to come up repeatedly this semester. So, getting started, we're talking about trigonometry. Trigonometry, as indicated by the TRI, starting that word, is in a sense the study of triangles. But we're also going to spend a significant amount of our semester here discussing circles. So we're going to see good reasons why we should be thinking about circles in relation to triangles here in our coming sections. But what we really want to be comfortable with is thinking about things like angles and how do we measure angles and how do we use angle measures to help us out with some calculations associated with circles. We'll spend next video discussing triangles, right triangles specifically. So, angles in standard position measured in degrees, also known as stuff people are already generally pretty familiar with. So, let's start with a little bit of a technicality on a definition here. If I were to ask you to think of some 2D shapes made of straight lines, what I know is that everybody is thinking of closed polygons when you think of that. However, we should consider the possibility of, if I said to you a 2D shape with 3 sides, I think that a vast majority of us are thinking of things like triangles. but maybe you should kind of expand your mind a little bit to think of like this being a three-sided shape right there as well. That is a three-sided shape. It is not a closed polygon because it does not come back to connect with itself, but it's certainly an object that is comprised by three connected straight lines right there. The reason why I'm suggesting this kind of weird idea here is because our first topic of this semester is to discuss like what is an angle. And the slight distinction that I think is worth noting here is that an angle is not an amount of measurement that we have. The angle is actually the shape that's being created. An angle is a two-sided, non-closed, non-polygon shape, right? So an angle is a 2D shape that's made by two rays, right? So here is the shape of an angle. We say that this angle, this shape, has measure, and we measure the openness of that shape, and we typically do this in degrees or what we will call radians. I think that everybody in here, I'm assuming, is reasonably comfortable with the concept of degrees of an angle. I am also assuming that most of us are not super familiar with the concept of measuring an angle in radians. That is one thing that we will define today, and it's something that we will use very consistently throughout the course of the semester here. So degrees and radians are going to be our two essential measurements of an angle. And to help us kind of get in tune to thinking about what is a radian and why do we have multiple degrees of measurement here that we're going to use, you should think about temperature and the comparison between Fahrenheit and Celsius, right? So let's kind of stop and think about our analogy here for a second. There's a lot of different ways that we can measure temperature. And again, the temperature is not a feature of this class at all. We're trying to talk about angles, but I'm trying to set up an analogy here. Lots of different ways that we can think about measuring temperature. Each of the measurement systems has pros and cons, and each of them has a scenario in which it's probably the most appropriate. And while that's technically sort of like an opinion, it's sort of like, if every professional in a field has the same opinion, then that sort of becomes like the standard that happens there. And we've got a similar thing with temperature as we do with angles of measure here. So the three most common ways that temperature is measured is in Fahrenheit, which we use in the US, Celsius, which most of the world uses in a more of a metrics setting there, and then Kelvin. And I think that a lot of people are a little bit less familiar with Kelvin. I like to describe these three different systems of measurement as Fahrenheit this is measuring how humans feel, right? The reason why Fahrenheit is a good measure is because most of the temperatures on Earth that are experienced are somewhere in the span between 0 and 100 degrees Fahrenheit. Those are most of Earth's temperatures a lot of the time. And so that 0 to 100 scale of experienced temperatures is usually pretty useful to us. However, we know that like almost every single day, most people interact with things that are over 100 degrees Fahrenheit, like your coffee or if you boil water, stuff like that, right? So Celsius is a little bit more of a good descriptor for some of those more physical things, right? I like to think of Celsius as measuring how water feels, right? Celsius goes on a scale where 0 is the freezing point of water and 100 is the boiling point of water. So in that setting right there, 0 to 100 doesn't really describe the span of temperatures experienced on Earth. It describes sort of the span of relevant temperatures for water, right? So Fahrenheit is a pretty good scale for people. I've got to actually say, I've spent a lot of my, this is my seventh year as a full-time math professor. I've spent a lot of my professional life railing against the use of standard measurements. Feet and inches and miles kind of drive me nuts. I think that our country would benefit if we transitioned into using all metric measurements. I think the most the only non-metric measurement that I am still interested in sticking around is Fahrenheit. Because Fahrenheit is a broader span as well, right? So Fahrenheit, you should notice we go from 32 to 212 from freezing to boiling. That's a wider span than the 0 to 100 that Celsius gives. So it allows us a little bit of a finer measurement between temperatures, which is also a little bit more helpful for, again, describing how humans feel. So Fahrenheit, I think, is still pretty appropriate, even though it doesn't fall within the metric system of how we typically measure things. That makes all of our math work out nice. Now, Kelvin is the same as Celsius, except you just subtract 273 from all the numbers, Because what Kelvin is describing is beginning at zero being literal absolute zero, meaning an absence of motion of the atoms within that substance right there. So a little bit technical. Don't worry about Kelvin. Obviously, like I said, we're not focusing on temperature in this class, but this is measuring how atoms feel. Is really what this is doing. If you are 0 Kelvin, then that atom is literally not moving. It has no sense of vibration or motion whatsoever. Lots of motion with atoms is associated with lots of temperature that's out there. So again, three different scales as to how we measure temperature. Each of them have a setting in which they are the most appropriate scale to be used. Even though, and again, the reason I think this analogy is important because I even include Fahrenheit as having a reasonable place where it's the only kind of non-metric measurement that I'm kind of a fan of sticking around right there. So similarly, we want to think to ourselves equivalently, there's a distinction between how we measure angles, and there are pros and cons to all of them, and there are most useful scenarios for each of them here. So the two that are by far the most common are degrees and radians. And similarly, there is a different one that's out there. I know that I'm assuming like half of you don't even know what Kelvin is. Similarly, I'm assuming that most of us haven't heard of a tau measurement here before. So I put a little question mark next to it. I'll explain it super briefly. It's something that sounds like a good idea until you actually do a lot of math, and then it's not, and that's why we don't use tau. But in any event, degrees are useful because degrees, we know that there are 360 degrees in one full revolution, right, or in one circle. The reason why degrees are reasonable is because it's easy for humans to think in terms of fractions of degrees, right? So when humans think about angles, degrees is useful for like visualization. I can visualize 90 degrees pretty easily. And therefore, if you were to say to me, visualize a 40-degree angle, I can think about that being a little bit less than 90 degrees. And therefore, that kind of helps me do my visualizations, all right? So I'm going to say here, useful for humans to visualize amount of an angle. Radians, on the other hand, are going to be maybe slightly less useful. And again, we're going to define radians here in a minute, do some computations with radians. So I just want to kind of like state why there's these distinctions. Radians are going to, it turns out now, part of our justification for why we like radians so much is a little bit tied to calculus. It makes some things work out nicer for calculus. The bottom line is that this is more useful for computations with angles. And what I'll just say is, if you were to attempt to do all of calculus using angle measurements in degrees, what that would do is it would introduce lots of extra constants that you're multiplying by and adding by in scenarios that we can eliminate if we would just do all of our computations with angles in radians. And so the reason why radians end up being preferred is because they make a lot of our computations work out to be a lot cleaner. And that hopefully I'm hoping that you agree with that being a good motivation for choosing to use that system of measurement. The tau thing, we're definitely never going to discuss, but I brought it up just because there's three standard measurements for temperature. There technically are three things that some people use for angles out there. Tau, I'm just going to say nobody uses this. And I will say 1 tau equals 1 revolution, right? So this is like a reasonable concept to say, well, if it's just 1 lap around the circle, why don't we just call that 1 and give a unit of measurement to it to call it 1 tau? 2 tau is 2 laps around a circle, stuff like that. A quarter of a tau, that would be like our 90-degree angle. It turns out that this just has the same issue of degrees in which it just ends up introducing additional terms to have to work with once we finally get into doing like real math with trigonometry ideas out there. And so while that does sound like a nice, easy to remember system right there, it just ends up making all of our computation more difficult later. And so that's not really doing ourselves any favors right there. So in a sense, radians are sort of like the preferred way to measure angles here. But just like with Fahrenheit and Celsius, if you know one of them, you can just easily do a little bit of math to get to the other one, right? There's conversion formulas for these. We will build our conversion formula between degrees and radians today. I know that all of us are going to be already comfortable with thinking of angles in terms of degrees, so we do want to do that. But it's also going to be important that we are able to convert our thoughts then into radians because it's going to make our computations nicer for us. So thinking in terms of radians is going to be one of the very important things that we're all going to want to do this semester, is to kind of try and like take on this new system of measurement and learn to think in terms of that. And it will provide us certainly some mathematical benefits down the road of making things a little bit easier for us later. So We're going to want to define radians. We haven't done that yet. All I've said is it's an alternative to degrees, and it makes math a little bit easier when we do things in terms of radians instead of degrees. We will define what is a radian, how do we convert between radians and degrees. We're going to talk about that in a second here. I just want to say a few more things about angles here. All right, so this paragraph right here just saying most of you are familiar with degrees. You should work to make sure that you're capable of thinking in terms of radians. We'll use them both approximately equally this semester, approximately, but both of them very regularly, and you are certainly going to expect to be equally comfortable at using both systems of measurements. There should not be any scenarios this semester where I give you a problem in terms of radians and that somehow prevents you from doing the problem, right? These should be systems of measurement that we're capable of working with equivalent here. So again, let's talk a few more things about angles in general first, and then we're going to go ahead and come back to this idea of what is a radian. All right. So to help provide us some consistency in how we measure angles, it's very typical that when we're drawing angles, we place them in what is referred to as standard position. Standard position means that we are imagining being in a two-dimensional coordinate plane where we place the vertex of the angle at the origin. We place the initial side of the angle on the positive x-axis. That is a ray, a line that extends forever in one direction on the x-axis. This is our initial side. And we place the terminal side of the angle elsewhere. Right? This is our terminal side. Right? So in this case right here, terminal meaning ending side right here. So in this case right here, here is our positive angle, theta, right there. Let's talk about a couple other things, right? Okay, we're going to talk about our directions and our quadrants here in 1 second. So this angle that I've just drawn, it is in standard position because its vertex is at the origin and its starting ray, right? The first side of the angle is on the positive x-axis right here, right? X-axis, y-axis. The terminal side of where it ends is helping us measure the amount. The measure of the angle is how much did this open from the initial side to the terminal side right there. Very importantly, notice that I did draw an angle, draw an arrow indicating the direction of rotation that was experienced to achieve this angle here. And we do want to talk a little bit about that distinction down here. So a couple things here. Given that an angle has measure theta, so the most commonly used variable to reference angles in trigonometry is Greek letters. We'll very typically use Greek letters to measure angles. We'll use both theta and phi, which is like theta except as a vertical stick instead of a horizontal stick. We'll use that once we have more angles to talk about. We'll also use alpha, beta, and gamma when we have 3 angles to talk about, like in a triangle. That's a little bit more typical, just to have like sort of 3 related things. That's just ABC in the Greek alphabet that's out there. So theta, super, super, super common. You're going to write 1,000 thetas. You're going to see me write 1,000 thetas this semester. It's the measurement of the angle. So given that an angle has measure theta and is in standard position, we would say that theta lies either in a quadrant of the grid or on the x or y axis right here. In this case, we would say that theta is in the first quadrant. And I'm going to write how we number our quadrants here. In any coordinate grid, we've got our x and our y axis here. Our quadrants, we number going counterclockwise from the upper right quadrant. So this is, I'm using my Roman numeral there. It's our first quadrant, our second quadrant, our third quadrant, and our fourth quadrant. These are the 4 quadrants that that every graph is essentially broken up into based on their axes, right? So it's very common to use Roman numerals for quadrants, but if you were to say like Q3, I know that you mean quadrant 3, so I'm pretty okay with whatever notation there, but very common to use Roman numerals to reference quadrant. And I kind of think that's a good idea because it just kind of helps there not be any confusion about what you're talking about. If I see Roman numerals, that can really only be referencing one thing. It's the quadrant in which it lives. So let me kind of give some examples right here. Positive angle and I'll write this as in Q2. So here's an example of an angle that is in the second quadrant. There's my first ray, my initial side and my terminal side. And here again, I'm going to indicate this arrow to help indicate what was the direction of rotation. As I just said a second ago with our quadrants are numbered in counterclockwise order. This direction of rotation, this counterclockwise direction, is what we consider to be the positive direction of rotation. So this is a positive angle because we rotated in the counterclockwise direction. We could also have a negative angle on the y-axis, maybe. And again, I'm just kind of giving some examples right here. Uh, an example of a negative angle on the y-axis might be, so again, I'm going to put my angle in its standard position, so it's on the positive x-axis for the initial side. If it's on the y-axis, then that has to mean I'm like on this line right here. And so notice in this case right here, we're rotating clockwise, right? So here my angle is still measured as theta, but here theta would be a negative number. It would be negative 90 degrees because here we rotated in the clockwise direction. This is our negative degree or negative direction of rotation. Counterclockwise here is our positive direction of rotation. So this angle theta right here looks like it would be about 90 degrees and then maybe another like 45 degrees. So this is maybe like positive 135 degrees. So I'll maybe just say here theta is approximately positive 135 degrees. Here it looks like we went in the opposite direction. We'll refer to this as a negative angle. And that just helps give us an idea of direction, right? So don't get too hung up on positive versus negative. It's really almost making more of a distinction between clockwise and counterclockwise. It's just a binary choice. There's two directions we can go. We will indicate those directions with positives and negatives here. So this would be an angle of negative 90 degrees. That was just indicated in that drawing right there. Here I would say that theta is on the y-axis. Here I would say that theta is in the second quadrant right there because the amount of rotation from standard position would place the other ray in quadrant 2 right there, right? So just some examples about drawing angles, thinking about positive and negative directions of rotation, thinking about describing where an angle is by describing either a quadrant or notice the only way that you're not in a quadrant is if you're on one of the boundary lines right here. So those are the axes. So that's basically to say every angle is in one of the 4 quadrants or on one of the 4 axes right there, positive or negative x or y axis. So just some like standard angles that we should all know. I'm assuming that mostly everybody is down with these. If not, these are pretty simple. One full revolution, one way all the way around, 360 degrees. Let's super briefly talk about why this number is not specifically meaningful. This was a random number that, okay, it's not random. This is a number that was just picked by humans. There's nothing inherently 360 about circles or full revolutions. 360 is just a really nice number because it's highly divisible, right? 360 is divisible by 2, it's divisible by 3, it's divisible by 4, it's divisible by 5, it's divisible by 6, it's not divisible by 7, it's divisible by 8, it's divisible by 9, it's divisible by 10, not divisible by 11, it's divisible by 12. It's got so much divisibility. It's divisible by 15, 20, so many numbers out there. So that's why this is nice for like humans thinking in terms of angles. It's really easy for me to think about fractional amounts of 360 easily without having to go into weird fractions or decimals or anything like that, right? So 360 degrees is sort of arbitrarily selected, right? It kind of could have been anything, but it made it a good choice. It really helps with mental math. That's why 360 is a pretty nice number. I do also think that there are some like original ties to this being near to 365 for number of days in a year for like calendar purposes. I'm not quite 100% on that one, but I think the divisibility of the number 360 is good enough reason to say, hey, this is a good number of units to use to break things down by. So therefore, 1 degree must therefore represent 1/360th of a revolution out there because it's 1/360th of a total number of degrees in one revolution. We refer to 90-degree angles as right angles, right? That's the guys that are going. Oh, by the way, right here, I could start with a ray and then do a full rotation around for theta. That's 360 degrees, where this initial side is the same as the terminal side location right there. One full revolution, there's our 360. Our right angle for 90 degrees right there, I think we're all relatively familiar with that. Very common to use that little square in the corner to indicate that even if you're like me and not super great at drawing things, that you can say, I meant that to be a 90-degree angle. That's what that little square in the corner means to us right there. Straight angle, which is sort of a stupid phrase right there, but I guess it kind of makes sense that as you're opening up the two rays that make an angle, at one point they might be pointing in perfectly opposite directions right there, in which case they really sort of make like a straight line. So in this case right here, we would call this a 180-degree angle, which is really sort of like a straight line, and so therefore it's typically referred to as a straight angle right there, 180 degrees. Some other things, a little bit less important here. Minutes and seconds are breakdowns of a degree. So 1 minute is 1/60th of a degree, just like a minute is 1/60th of an hour. And then 1 second is 1/60th of a minute, which actually identically matches how we measure time. And those two things are made to match on purpose. Also, nice little sort of trivia. Why do we call seconds seconds? And that is because it is the second breakdown of a degree, or second breakdown of an hour right there. So that literally is referencing like first, second, third. When we call seconds seconds, it's the second breakdown of an hour, hours to minutes to seconds right there. So these are not like these aren't going to really come up much at all this semester. I will say minutes and seconds are generally just not really used in the real world outside of navigation. Like if you're going to be a pilot, it matters that you're able to think in terms of minutes and seconds, and that's about it. I don't want to say like nobody uses minutes and seconds, but like mostly nobody uses minutes and seconds. And the bottom line is rather than using minutes and seconds, we can just use decimals on our degree counts, right? Like 5.67 degrees. That's really like 5 2/3 degrees. That might be like 5 degrees and 40 minutes right there, because 40 out of 60 minutes would be 2/3 of a degree. Stuff like that. But I'm not super worried about our minutes and seconds. You should be aware that these are 60ths of their previous measurement. That's it. I'm not going to throw a bunch of degrees or sorry, I'm not going to throw a bunch of minutes and seconds at you this semester. I'll bring it up once in an example today, and that might be the only time I mention it this semester. It's good to know that they exist, but we won't use those since this is not a class on navigation. This is a class more broadly on trigonometry. So let's talk radians. What is a radian? We're going to want to use them half the time this semester. We do want to be equally comfortable with radians as we are with degrees. So we want to get to defining a radian here. So radians have a pretty nice like construction. The definition of, because like the definition of what's a degree is weird. If I said to you what's 1 degree, you'd say to me, well, it's 1/360th of the amount of rotation in a circle. And that's kind of weird, right? That's sort of random in a sense. Radians are, in a sense, a little bit more smartly constructed. They have a little bit more of like a firm basis of which to measure it in a way that sort of makes sense, right? So there's sort of like a step-by-step process that we can follow to like draw 1 radian just by instructions here. So let's do that, which is a little bit harder, right? If I said you draw a 1 degree angle, that's like weird to do, but drawing an angle that's 1 radian is a little bit more natural. So here's what we're going to do. We're going to draw a circle. Oh, hey, that could have been worse. I just say I consider myself pretty masterful on a whiteboard with my shapes. And using my digital stylus I'm a little bit less masterful with drawing good shapes here. So you're going to see a lot worse circles than that this semester, I can assure you. So begin with a circle of radius r at the origin, right? So I'm going to do myself, well, okay, all right, I'm not going to do, I was just suggesting there. Here's our radius of our circle, right? The radius of the circle, meaning the distance from the center of the circle to the perimeter of the circle. The radius, the definition of a circle is the shape such that all the points on the shape are the same distance from the center, and that's our radius r right there, right? So I've marked the radius r of our circle. What we want to do is we want to pick a location on the circle, and we want to go exactly this distance along the perimeter of the circle. So the important thing to notice is that here, r is a straight line distance. I want to go this amount of curvy distance along the perimeter of a circle. The amount that we'll traverse right here, that angle, will be exactly 1 radian, right? So I am saying here, we could do this from any point on the circle. I'm going to pick like a convenient point, like that point, sort of our initial point right there on the circle where we start measuring our angles from. And if we kind of do this amount of rotation up to here, what I'm trying to sweep out is a arc length of the circle that's exactly as long as 1 radius. right? So, and I'm kind of preempting myself a little bit right here. Typically, the letter S is used to denote arc length, the length along the perimeter of a circle, but just a chunk of it, right? So this is an arc of the circle, is what I've kind of bolded in black along the edge right here. This is the arc, and if our arc length that we are sweeping out with our angle, if that arc length right there, this length, this curvy length, is exactly the same as the radius length, then what that says to us is that this angle right here that we've made, that theta right there, that theta is exactly the definition of what we mean when we say 1 radian. It's the amount of angle required to sweep out 1 radius's worth of arc length, right? I'm going to say that again since this definition is important. 1 radian, 1 radian is the amount of angle required to sweep out 1 radius's worth of arc length along the perimeter. So no matter what your radius of your circle is, that might be 6 units long. That says start at any point on the circle and travel along the border of the circle for 6 units then, if that's the radius. However much angle was swept out, that's our definition of 1 radian. All right. So the nice thing is that this is kind of easy to construct, but now maybe there's some like less obvious things that we want to answer about this guy right here, right? So I'll just say here, this theta is exactly 1 radian, right? So that's kind of what we were trying to define. What is a radian? It's the amount of angle required to sweep out 1 radius's worth of arc length. So one thing that we might want to know then, since we're sitting here talking about circles, the most common fact that people know about angles and circles is that one circle is 360 degrees. So therefore, to me, a very natural question to ask is, well, then how many radians are in a circle? If radians are measuring angle and degrees are measuring angle, and 360 degrees makes a full circle, how many radians make a full circle? I'm just trying to get some like side-by-side comparison. This is like me saying, I know that water freezes at 32 degrees Fahrenheit. What does it freeze at in Celsius? Oh, 0 degrees Celsius is equivalent to 32 degrees Fahrenheit. We're trying to kind of get our analogy set up here, our relationship set up. So here's the way that I'm thinking about this, and I want to reference this picture that's up above right here. Importantly, the perimeter of a circle is what we refer to as the circumference of the circle. And that formula for circumference, this is just our basic circle facts right there, is 2 times pi times the radius. That will always give you the full perimeter length of any circle. All you have to know is the radius. So if the radius of a circle is 5 feet, then its perimeter is 10 pi feet. 2 times 5 times pi, right? So what we want to do is use this information to help us figure out angles, right? So here's what I know. If we sweep out 1 radius's worth of arc length, that is 1 radian of angle. I know that we need to do 2 pi radiuses to get all the way around. Therefore, we need to do 2 pi radians an angle to get all the way around. So this says, so let's say since 1 radius of arc length sweeps out 1 radian, then it must be that 2 pi radiuses must sweep out 2 pi radians. And 2 pi radiuses, that's the whole thing, right? 2 pi radiuses, that's exactly the full circumference of the circle. So it seems like 2 pi radians is the same thing to us as 360 degrees, right? So this is our first radian fact that you're going to want to go ahead and burn into your brain right now. There are 360 degrees in a circle. There are 2 pi radians in a circle. Those two statements are identical statements. That's literally the same thing as me saying water freezes at 0 degrees Celsius, water freezes at 32 degrees Fahrenheit. Identical statements, just two different systems of measurement right there. So this is a fact that you will use in your brain about 1,000,000 times this semester right there. 2 pi radians, that's one full circle right there. So I'm going to kind of weave a couple ideas in together here. We still want to talk a couple more things about getting comfortable with using radians, but I want to kind of come back to a special word that I used up above right there, and that was arc length. We referred to this arc length right here as being a piece of a perimeter or a piece of a circumference, right? Arc length, the actual length itself, is always denoted with S, just like we always use R to denote radius length. S is always going to denote arc length. So above we use an important word, arc length. An arc of a circle is one piece of the perimeter of the circle. And by the way, I'd like to identify that a circle is just the edge, whereas a disc is like the whole thing, including being filled in right there. So I might, I don't know, I can't really actually draw this right there, but that might be that solid thing. This is like one arc length right here, right? And I would notate that as being S, and I might indicate that as a radius right there. And what you can see is maybe there's like some angle that's associated with that arc length right there. So one of the things that we're going to want to be able to do right now is figure out how to compute how long some given arc length is based on the angle that was swept out and a radius, right? So what I want to kind of do to kind of, as we're getting used to using radians here, this is sort of my example that's going to lead us through all the other things that we want to look at right here. Is I'm going to state this example problem. What I want to say right now to you is we're going to go through several layers of needing to kind of figure some things out to get to this guy right here. So we're not going to directly answer this example right now. We're going to let this lead us to a few more questions of things we need to explore. We will answer this. It's just going to take us a couple ideas to get between stating it and answering it. So suppose a circle has a radius of 5 inches. If we sweep out, or our math word for this, I feel like this is like unnecessarily weird of a word, but our book uses it all the time, so I want to use it. To subtend an angle is to sweep out an angle right there. So that word subtend means sort of like to traverse rotationally. Right? If we sweep out or subtend an angle of 30 degrees, what was the length of the arc of the circle that we've swept out, right? So picturing our diagram right here, our radius is 5 inches. The angle that we're picturing traversing is 30 degrees, right? Not a huge angle right there. What I want to know is what was this curvy length that was traversed by maybe like a point that was sitting right there at the end if we rotated that radius of 5 by 30 degrees right there. We know it's just a piece of a circle, so that should be really helpful for us since circles aren't too terribly difficult for us to discuss geometrically here. But we want to get a little bit more of a general descriptor of how to think about this. So to start with right here, what I'm going to do is I'm going to draw a circle with two general angles and their associated arc lengths right there. Man, I set myself up to draw a lot of circles today. I could have just, oh man. Oh, that's the nicest circle I've ever drawn with a digital pen. If you need to take a screenshot right now, go ahead and do it. Ooh, that's a good one right there. So I've got a circle for myself right here. Oh, it's a good looking circle. I'm going to place my center of the circle right there. And again, notice that the radius of the circle is the exact same everywhere. So what I'm going to do is I'm going to mark on this circle two different angles that have been swept out and their associated arc lengths. Right? So I'm going to put one of them on here, and I'm intentionally going to make this one look like about one radian's worth right here. Right? So this is our radius. But the radius is the same everywhere, right? So what I'm picturing here is this arc length that I've just drawn right. Oh man, I can't believe I'm messing up my good circle now. This arc length right here, I'm going to go ahead and I'm going to call that S1. It's one of our arc lengths. I'm going to make another one in a second. We'll call that S2. The angle that I've swept out here, we'll call this theta1. Now I'm going to draw another one on the same circle right here so we can make a little bit of a comparison. Notice that this angle is smaller, and consequently, the arc length itself is also smaller. So I'll call that theta2. Now it's a little small right there. And we can call this S2 right there. It's our second arc length right there. So the really important thing that we want to see here is that I guess I'll scroll down a little bit. The essential relationship to see from this drawing is that the size of the angle, the measure of the angle, is directly proportional to the length of the arc. The more angle you get, the more arc you get. And those are going to be like linearly related to each other. If you double your angle, you get double the arc. If you triple your angle, you get triple the arc. If you half your angle, you get half the arc that's out there. So what that means to me is that I should be able to set up some ratios that are equal to each other. Since these are always going to be proportional to each other, it should be the case that theta 1 over S1 is equal to theta 2 over S2, right? These should always remain within proportion to one another. So their ratios are always going to be equal to each other, whatever they're going to be. Right? Now, suppose that one of the angles that I drew, which I kind of did, I kind of set this up intention to look like theta 1 and S1 are in fact sitting here, theta 1 being 1 radian. Now, suppose that theta 1 is 1 radian, right? Then what that's telling me is if theta 1 is 1 radian, and by the way, a very important thing here, I'm measuring theta in terms of radians right here. Well, remember what the definition of a radian is. A radian is the amount of angle that we sweep out when our arc length is exactly equal to 1 radius's worth of length. So that says to me, if we're going to go ahead and do like our hypothetical, if theta 1 is 1 radian, then what that means is that S1 is R. Right? That's the definition of a radian. A radian is the amount of angle it takes to sweep out 1 radius's worth of arc length. So this arc length must be 1 radius, or just R. So knowing that theta 1 is 1 radian tells us that our first arc length must just be R. It's 1 radius of the circle. So this allows me then to rewrite my above proportion statement up here as theta 1 is 1, S1 is R, and here we're getting theta 2 over S2. All I want to do now is just do a little bit of math right here. I'm just going to do a little bit of algebra. I just want to multiply my S up to this side. I'm going to get S over R equals theta. And then I'm going to go ahead and multiply my R over to the other side. S equals R theta. I did drop my subscripts of 2, but that's because I didn't need to distinguish between my two thetas and my two S's anymore, since I called one of them 1 and R. And so just by doing a little bit of math, then this formula now should give us our specific relationship between amount of arc length, amount of angle, and radius of the circle. So this is our arc length formula, and it comes by understanding that the amount of angle swept out will always be proportional to the amount of arc length that was swept out, right? One is an angle measurement, one is a perimeter measurement, but they're always going to be proportional to each other. And using that information, we're able to deduce that it should always be the case that our arc length is equal to the radius times the amount of angle. But the one really important thing here was that this was only true based on the fact that we measured thetas in radians. So this formula is good all the time as long as your angle is in radians. You have to be in radians. This formula does not work if you use degrees as your measurements. So by the way, right there, right away, this is one of our first examples of why math is actually very often easier when you're using radians than degrees. If I'm picturing an angle in my head, I think in terms of degrees. If I'm doing math with angles, I want to be in radians. And this is our first example of that being the case here. So this equation, S equals R theta, relates three quantities: the radius of a circle, S, the length of the arc of a circle, and theta, the angle associated with the arc, which must be measured in radians, right? So this is good for us because I asked us in our example previously to compute an arc length. We've now figured out how should we compute arc length, but our problem is that in the example that I originally gave, I gave you an angle that was in degrees. So it looks like we sort of know what to do now, but our problem is we need to convert our degree measurement into a radian measurement so we can actually do the problem here, right? So our still standing issue is that our angle is given in degrees, but our arc length formula only accepts angles and measured in radians. We would like to be able to convert between degrees and radians, just like we can convert between Fahrenheit and Celsius. I'm sure all of us have converted once or twice between Fahrenheit and Celsius in our lives at least. It's like the 5/9 times the Fahrenheit temperature minus 32 or something like that, and I always forget which ones get the parentheses. The point is, our conversion between degrees and radians is going to be easier than our conversion between Celsius and Fahrenheit. So if you remember doing that conversion, it's not hard. This one's just going to be even easier right here. So to establish our rule for converting between radians and degrees, what we want to do is identify two measures that we know are the same in each unit of measurement and set them equal to each other and see if that's helpful for us. So what I'm going to do here is I can say that one full revolution can be described two different ways. 360 degrees is one full revolution. That to me is the exact same as what we said a second ago, 2 pi radians, which I'll just briefly denote as rad right there for radians, pretty common abbreviation. Although I should say, this is a thing I might as well just say now. In general, if you ever see pi show up in an angle measurement, that means it's in radians, unless it very specifically, there might be one time that the book will be a total jerk to you and do something like pi degrees like that. That is literally meaning that that problem only exists to specifically see if you get confused by units right there. I can't think of a time where pi degrees would ever be a measurement that would ever occur in any setting ever. I will not try to intentionally confuse you like that, but this is just to say it's not like I'm going to write rad next to every single angle measure for this semester. If there's pi's at all, it's radians. You can always just go ahead and assume that, right? So what I'm going to do is I want to build a conversion factor. I know that 360 degrees is the same thing as 2 pi radians. So what I'm going to do is I'm going to do algebra both directions. I'm just going to do division both ways. One thing I can do is I can divide by 2 pi radians on both sides to get the statement 360 degrees over 2 pi radians. And what does that equal to? Well, it's equal to just 1 because I divided 2 pi radians on both sides. 2 pi radians over 2 pi radians. That's a unitless 1, and that's really important to us for a reason I'll explain in 1 second here. Similarly, we could go the other direction, right? I could divide both sides by 360 degrees. That would leave me with the statement 1 equals 2 pi radians over 360 degrees. The reason why these are important equations for us is because this is now giving me a different way to write the number 1. The reason that the number 1 is a very special number is because it's the literal only number that there is where you can multiply numbers by it and they don't change, right? So I'm allowed to multiply anything in the world by 1 because it won't change it. But what that really means is multiplying something by 360 degrees over 2 pi radians doesn't change what the value is. It only changes what degree of measurement we're using to measure the angle in. So these are our two conversion factors that we can use. And by the way, typically people often, I should say, not typically, often people will reduce these. We can do a little bit of fraction reduction. 180 degrees is apparently the same thing as pi radians. And we get the same thing over here. Pi radians per 180 degrees. So this is like our multiplicative conversion factor here. So what we can do is we can use this now to convert 30 degrees to radians. And once we've got that, we can then use our formula to finally actually answer this question. So let's go ahead and do that. So we're starting with the quantity 30 degrees. What I want to do is use one of these conversion factors that we've just built for ourselves here, right? One of these statements right here to help turn my degree statement into a radian statement. Right now the units are degrees. I want to get rid of the units of degrees and introduce a new unit of radians, right? Typically, I put a little like line here because I know I'm about to multiply by a fraction. There's like a 1 down there. I'm not really worried about that. It's a 30 degrees out of 1 or something like that. The point is, I want to cancel my degrees units. This is the thing I want to go away is the degrees stuff. So I want to multiply this by a fraction that has degrees on bottom and has radians on top so that the degrees and degrees cancel, leaving us with just radians. Therefore, it looks to me like this is my best case scenario right there, right? This has, oh, wait, what is that right there? What am I, crazy? 180 degree radians. That doesn't even make sense. So the reason why this is a good conversion factor for me in this case right here, pi radians per 180 degrees, is because now my units of degrees and degrees cancel, top and bottom, just like any other fraction value would. This leaves me with 30 pi over 180 radians. And notice that very conveniently, this is why we like degrees the way that we do, is because this simplifies very nicely. These zeros sort of cancel together. 3 over 18 is 1 over 6. So I would say that this is 1/6 pi radians, or it's much more typical for us to just mash that pi in there, pi sixth radians. So it seems to me that 30 degrees is the same thing as pi sixth radians. And again, that's just like me saying 32 degrees Fahrenheit is the same thing as 0 degrees Celsius. They're both the temperatures at which water freezes, right? Here, 30 degrees as an angle could also be measured in radians. Pi sixths is how many radians are equivalent to 30 degrees that are out there. Right? So we have converted our angle into radians now. So now we can finally answer the question. What is the length of the arc of the circle that we've swept out? We have the formula S equals R theta. We know that the radius is 5 inches. We know that our angle, measured in radians, because this formula only works in radians, is pi sixths radians. And this allows us to make the statement then that S should be 5 times pi sixths, which we could write as 5 pi sixths looks like my exact answer, but that's not super helpful. Usually when I'm measuring length, it's not helpful for me to have things like pi in there because I want it like that. I can't picture how long 5 pi sixths is. So I'm going to go to my calculator here. 5 pi divided by 6. My calculator is telling me very close to 2.618. And what? We measured that in inches right there. All right. So we did a couple really important things here. We figured out what our formula should be on our own to compute arc lengths based on radius and angle. We figured out on our own how to convert between radians and degrees by just saying that since 360 degrees is the same thing as 2 pi radians, we can do the division either direction and recognize that what we did here is these conversion factors are the same as 1 because we divided in both cases by the equal value on both sides. So things like 360 degrees divided by 360 degrees, 360s cancel, degrees cancel, left us with the number 1. What we did here is the reason it was legal to do this multiplication is because we were just multiplying 30 degrees by 1, which is just 30 degrees. Multiplying 1 doesn't change our amount, but we multiplied by a special version of 1 that did change sort of our perspective, right? So the amount is the same since this multiplication was just times 1, but it did allow us to change perspectives, change units of measurement by doing that. So these are our conversion factors that are available to us to convert from degrees to radians or radians to degrees. All you've got to remember is that if you currently have degrees, you want to use the conversion factor with degrees on bottom so that the degrees and degrees cancel, leaving you with radians. And later, when we go to convert from radians into degrees, going the other way, you'll want to pick the conversion factor that has radians on bottom, so that radians and radians cancel, leaving you in terms of degrees up in the numerator. All right? So there we go. We did like our first real example right here. So let's cruise through a couple other things, and then we'll look at one last example, and we'll call it a day here. So the most important angles for us to know this semester, I've listed them here. Why these are going to be the most important angles isn't super obvious right now, but as we get into our discussion of right triangles, there's a couple right triangles that have some special properties, and we're going to want to identify those right triangles. These are just the angles that make stuff work out nice, and so these are really good like guideposts for us. They're just good breakdowns. This is like, we like to measure things in halves and quarters, but it's not so typical in our life that we measure like 1/7 of something, right? Similar thing here. These are just going to be convenient breakdowns for us that are comfortable angles to use. We'll see a little bit more of why once we get into our right triangles out there. But for right now, let's just go ahead and talk about converting these guys into radians, making sure that we can picture the amounts of angle that we're looking at right here. So I'm going to do a whole bunch of conversions right here, drawing some angles, right? First of all, 0 degrees. This is like our 0 degree angle right there. This is our initial and our terminal side. This is an angle of 0. We didn't go anywhere. We didn't sweep out anything. Hopefully you are down with the fact that when we do our 180 degrees times pi radians, that we're getting 0 times pi. Well, guess what? That's just going to be giving me 0 radians right there as well. So we at least get that convenience. 0 degrees is the same thing as 0 radians right there. There's no rotation that's going on. And notice that it's actually a little bit different than temperature. Our sort of zeros for temperature, I like to think about freezing point of water. Those don't match up for Celsius and Fahrenheit. I think it's kind of weird that Fahrenheit doesn't at least match Celsius at either the freezing or the boiling point for water right there. But But again, Fahrenheit does do a good job of describing how a human feels. 0 to 100 are our common Earth temperatures. So in any event, let's do some more conversions. We just did 30 degrees a second ago. 30-degree angle, that's going to be 1/3 of a 90-degree angle. So I'd say something that looks about like that guy right there. I'm going to do my conversion with my 180 degrees over pi radians. My simplification here is that 30 over 180 is going to leave me with 1/6. So that will leave me with pi sixths radians right there as our equivalent right there. And by the way, these are ones where you will just know these common ones by the end of the semester. All the ones in this list, within a few weeks, I expect you to just be able to say, oh yeah, pi 6 radians, that's 30 degrees. I know that. You'll just see these enough. It will happen naturally with how much exposure you'll get to this. 45 degrees, another really common one right here. 45 degrees is half of a right angle. Ooh, that was maybe a little bit big right there. Pretty close, whatever. I'm eyeballing these guys right here. Again, we're going to do our same thing. Pi radians over 180 degrees. Notice that 2 times 45 is 90, and 2 times 90 is 180, right? So this seems to be 1/4 of pi right there, right? 45 over 180 will give us 1/4. So this will turn out to be pi fourths radians. This is another really common one. We're going to see 45-degree things all semester, but most of the time you're going to see it as pi fourths. And in your mind, you're going to be picturing that 45-degree angle. 60 degrees, next most common. It's clearly twice as much as 30 degrees. Hopefully you're expecting, therefore, to be twice as much as pi sixths. 2 times pi sixths. 2 over 6 is 1 over 3, so I'm expecting pi thirds here. So pi radians over 180 degrees. 60 over 180, or 6 over 18, is 1/3. And there's that pi thirds radians right there. So there we go. There's our 60-degree angle right there. Okay, maybe that looks more like 70 degrees to me, but still, whatever. I'm doing my... These are all comparatively correct right here. Next up, 90 degrees. One of our most important angles of measure right here. We know that 90 degrees is a right angle. Another thing I like to think is 90 degrees is 1/4 of a full revolution. If 2 pi radians is a full revolution, 1/4 of 2 pi is pi halves, right? 1/2 is 1/4 of 2. So I'm expecting to see here when I do my little multiplication with my conversion factor here to get that, right? 90 over 180 is certainly 1/2. So I'm going to get my pi halves radians right there. So when we have an angle that is opening as a 90-degree angle right there, that is pi halves radians is the same thing. Our last common ones, 180 degrees. We've already kind of seen this one right here. Hopefully you're not terribly surprised about this one. 180 over 180 is just going to leave us with pi radians. So pi radians is when we have opened up to our straight angle right there. This is our theta in this case right there. Pi radians, same thing as 180 degrees. Our next one, 270 degrees. Now notice this one is going to be drawn in a sense a little bit different. This says we need to do, notice that 270 is 3 copies of 90, right? So we're going to get to 90 degrees, then we're going to get to 180 degrees, and then we're going to get to 270 degrees down here. So this one's going to leave us with our final ray pointing down, but importantly, the angle theta is this sort of external angle here. This internal one, this would be negative 90 degrees right there, not positive 270 degrees, since it would rotate in the other direction right here. Notice here that if we do our conversion, pi radians times 180 degrees, 27 over 18 reduces down to 3 over 2 as a fraction right there. That's 3 copies of 9 over 2 copies of 9. So this is going to give me 3 pi halves radians. And again, kind of notice that if pi halves is 90 degrees, we just did 3 copies of 90 degrees. So we got 3 pi half radians right there, right? So realize that these do relate to each other in the same way that your degree relationships relate to each other right there, right? Finally, we know that 360 degrees is 1 full revolution. I know that 2 pi radians is 1 revolution, so I'm certainly expecting, when I do my multiplication, I get that. 36 divided by 18 is 2. And so we do get 2 pi radians here. And notice, and I want to sort of allude to something else that's coming here. Right? That was our full cycle there. Notice here that this looks a lot like my first drawing. But in my first drawing, there was no angle swept out because we didn't go anywhere. Here, we got back to there just being two rays pointed in the same direction, but this time we did experience rotation to get there. You might also notice that 720 degrees would be two full revolutions, and my diagram would look really similar again. Right? In a couple sections, we're going to come to define these as coterminal angles. 0 degrees and 360 degrees are coterminal. Co meaning together, terminal meaning end. They end together. They landed on the same location. They did it by a different number of rotations, but they landed on the same location. So 0 degrees and 360 degrees, and therefore also 720 degrees, those are all coterminal with one another. On a circle, they all land at the same spot, back at being that pointing to the right relative to standard position right there. Right. So again, I just want to do a bunch of conversions right there so you sort of get the feel of like the practice of this. You'll write out this conversion dozens of times this semester until you can kind of just do it in your head. These are the angles that you're going to see by far the most this semester. The degrees of them are all right here. All these radian measures, it is going to be essentially expected that you will have memorized that these are all equal to each other within a few weeks. But again, that's going to happen like naturally. Like you won't be able to avoid memorizing these. This will just happen by your exposure to this. So this isn't going to need to be like sit down with flashcards kind of thing. This is going to be like you'll just have to do enough conversions that you're going to be like, oh yeah, I remember that one. So again, these are by far our most common ones that you really need to know, be able to picture these in your head. If I say to you, picture a pi thirds radians angle, I often do that in conversion to think, okay, that's 60 degrees. I can picture that being more than 45, but less than 90. Stuff like that, right? So getting comfortable with these, this is going to be one of your things to do this semester. So we also need to be able to convert the other direction, though, right? Every conversion that we've done so far is to get out of degrees and into radians. Let's go the other direction, and then let's look at two last examples here. So how many degrees is 1 radian? I feel like this is a useful thing for like picturing what 1 radian is, right? Is 1 radian a lot? Is it a little? It's only one of something, so it sounds like a little bit. Should we think of it as a small amount of angle right there? Well, let's do the conversion. Notice that all of our previous conversions, we kept on doing pi radians over 180 degrees. We did that because we wanted to cancel our units, degrees on top with degrees on bottom. I now want to cancel radians with radians, so I want to flip my conversion factor. So instead now, I'm going to multiply this guy by 180 on top with pi radians on bottom. Now I'm going to cancel radians and radians, and it looks like it's going to be whatever 180 over pi degrees is going to be. I think that this one in particular is worth going to the calculator. We're going to get kind of a crappy decimal, but it's worth it for you to be able to like make a visual estimate in your head. How big is 1 radian, right? So if I go to my calculator and do this, 180 divided by pi, I know that pi is like 3.14, right? So about a third of 180. And I do get about a third of 180. It should be about 60, and I get 57.296. Right, I should make this approximately equal since I did just round right there. So it's just kind of good to know about what we're looking at. 1 radian is apparently like a little less than 60 degrees. And you definitely don't need to memorize this number at all. But I think it's worth remembering, like, yeah, it's about like 57 degrees, something like that right there. It just gives you like a visualization that helps. Because again, I know that most of us can picture angles in degrees and most of us can't yet picture angles in radians. So knowing how big 1 radian is in terms of degrees, I feel like this just helps me make some like mental images of how big stuff is out there. What's a lot more common though, so the reason why this was a weird conversion is because I gave you a number of radians that didn't have pi in it, which is pretty uncommon. Overall, most radian measurements are a fraction of pi or some multiple of pi out there. So let's see some of these here. So pi half radians, well, what I want to do is I want to be multiplying this same conversion factor, 180 degrees, over pi radians. Well, I'm going to get my radians in the numerator, cancel with my radians in the denominator. Notice very conveniently here, pi cancels with pi. And now all I'm left with is 180 over 12, which is going to give me, let's see here, 18 divided by 12 is 1.5, but I have an additional times, stick an extra zero, I'm multiplying by 10 is going to give me 15 degrees. So notice that some pretty clean degree measurements are referenced by pretty clean fractions of pi in terms of radians over there, right? So I did the conversion, found out that was going to be 15 degrees. We can do more like this, right? 180 degrees on top, pi radians on bottom. We're going to see radians cancel with radians, pi cancels with pi. All that we really have to do is do 180 over 60, and that's a pretty simple simplification. Zeros cancel because those are both multiples of 10. 18 over 6 is just going to give me 3 degrees. So it looks like pi 60ths radians is the same thing as 3 degrees. Pretty small measure in both cases right there. Finally, pi radians, well, I don't even need to do this one. I can just look up above. Pi radians, there it is. Looks like pi radians is the same thing as 180 degrees. A really good thing for you to remember in this case is that 2 pi radians is one full circle. So pi radians must just be a half of a circle, 180 degrees out there, right? So again, we could do this 180 degrees over pi radians. And I get pi cancels with pi, radians cancels with radians, and it just leaves me with 180 degrees. Nothing else to do there. Everything just canceled away. Right? And finally, we can get some like slightly weirder ones right here. Again, this is kind of unusual. It's very typical to see radian measurements be a fraction of pi or a constant multiple of pi. So this one's, I mean, there's nothing wrong with it. It's just don't expect to see things like 1.3 radians often. It's almost always given in terms of pi. So radians and radians cancel. I get whatever this is, right? 180 times 1.3 over pi. That's how many degrees this is. I don't know what that is. I just got to go to my calculator on this one here. 180 times 1.3, that's 234, divided by pi. It's going to give me 74.48. Again, I did some rounding right there. Don't over round. If you're ever unsure about roundings this semester, just round less than you were thinking about rounding. Typically, we want to keep on angle measures at least two decimal places on all these angle measures here. I think rounding down to less than 2 decimals, I basically just sort of consider that lazy. Like, you've got the decimals. You did it in your calculator already. Don't get rid of more than that, right? I'd say 2 decimals is sort of our limit on that one right there. Don't get rid of anything more than that. So again, doing our conversions here, the thing to remember is that we're always saying that things like 360 degrees is the same as 2 pi radians, and we're allowed to use that as a conversion factor either way. We often simplify it to be 1 pi and 180 degrees. 1 pi radian and 180 degrees are the same thing. And again, you're multiplying by that fraction. You have to decide what's the appropriate direction for that fraction. And the reason that you know which direction is by saying, I want my units to cancel. Here, degrees canceled with degrees to leave us with radians. That was good. Here, radians canceled with radians to leave us with degrees. So you just have to think about units and deciding what direction do I need to multiply my conversion factor by to get our new measurement here. So we got degrees, we've got radians defined, we've got arc length defined. We can convert between degrees and radians, which we need to be able to do to use our arc length formula. One other feature of a circle that I want to talk about is the area of a sector. After that, we'll do one last example that'll actually really just be about arc length, and then we'll call it a day here. So what about the area associated with one part of a circle, right? This is referred to as a sector. So as opposed to doing like arc length where we were talking like the perimeter, I'm now talking about like getting the area of a piece, right? So it's really saying like how much area is encompassed by sweeping out some certain angle versus how much length of the perimeter was swept out by some certain angle. So this is what we would call a sector, right? A sector is a amount of area associated with a circle, right? But it's only a portion of it, right? So the book gives us a sector area formula. I never use that formula. I always just think about it. I'm going to show you how I do this computation. What I'm doing is exactly equivalent to the formula that the book gives. I just never like give that students the formula and say use this formula because I don't. It's unnatural, and the way that I think about it is very natural. So let's just do an example, and you'll see exactly what I mean. So suppose a sprinkler can spray water up to 25 feet, right? So it's watering all the grass between at the sprinkler and up to 25 feet away. And as with most sprinklers, it's not spraying fully in a circle. It's only spraying some arc of your lawn, right? I think this is like the classic thing, like going out to move the sprinkler or something like that to get the whole lawn, right? So my question is, what area, like in square feet of my lawn, will receive water from this sprinkler if I just set it down in one place, right? So first things first, I need to be able to measure like 120 degrees. And I always like to break down angles like this into sort of like unitizing them in a sense. And when I say that, what I really mean is like these are all of my sort of like basic construction angles. I like to build all of my other bigger angles based on just these parts that are in like our 0 to 90 there, right? So, 120 is not in this list, but it seems to me like it's easy to make up 120 with like a 90 and an additional 30. That's how I think about 120 here. So when I think of 120, I like to think of this as like 90 degrees plus an additional 30 degrees. And so in that case, that helps me see that. And I'm going to draw an angle in standard position here, right? So there's my start. We're going to open up by like 90 degrees and then go an additional 30 degrees from that, right? So I'm picturing something like this for my overall angle. That's my 120 degree angle that I've just drawn right there. The other thing that's important is that we've got some, and what I really should do is sort of put some dots right here, right? Is that we've got that our radius here, I'm going to say theta equals 120 degrees. We've got that our radius here is 25 feet. And what I want to know is, if this is the chunk of my lawn that's getting water, how much area is this? So what we're talking about here is the area of a portion of a whole circle, right? The area of an entire circle, I was about to write my circumference formula again, not 2 pi r, we're talking pi r squared, right? So I'm sort of building from that. Pi r squared would give me the whole thing if it did 360 degrees. I only want to keep a fraction of that, right? I only want to keep a portion of the circle, 120 degrees out of the total 360 degrees. We only want a fraction of that area, right? We want to keep, well, what fraction of a circle did we encompass? Right? 120 degrees out of 360 degrees. Well, that's just 12 over 36. That's 1/3. Right? So it seems like if we want the area swept out by 120 degrees of a circle, that really just represents 1/3 of the circle because that's 1/3 of the number of degrees in a full circle right there. So all I'm going to do is just keep 1/3 of the area. And that's all we got to do here. Right? So our sector area should be then, we're going to keep our pi r squared. And I'll say here times the proportion of the circle. Right? And the good thing is we know all these numbers right here. So let's go ahead and do this guy. We've got pi times r, our radius is 25 feet. We're going to square that. So this right here would give us the area if the sprinkler did a full 360 degrees. It would be pi times 25 squared square feet. But we're only going to get 1/3 of that because our sprinkler only has a span of 1/3 of the number of the degrees in a circle. And by the way that I'm going to write this, I'm not even going to write the 1/3. I'm just going to say, and it was 120 degrees out of 360 degrees. That's just my proportion, 120 out of 360. We know that simplifies down to 1/3, right? So this is going to be pi times 25 squared. I know that one. That'll be 625. Get that out of your calculator right there. Times 1/3, right? So every time I'm doing sector area, I always just do the entire area of a circle and then multiply by the fraction of the circle that we're actually interested in. In this case, it turned out to be 1/3 of a circle, and the way that I knew that was because we had 120 degrees out of 360 degrees in a circle right there. And so if I go to my calculator, I can do 625 divided by 3, and I'm going to multiply that guy by pi, and it looks like I'm getting very close to 654.5. Oh, I just yelled at you for 2 decimal places, so I'm going to do that. If I'm rounding appropriately, it should be 0.50, and this will be square feet of the lawn that's associated with this guy right here. So let me show you what the book shows you for your formula and why I just don't do that. Where the book's formula comes from is exactly this exact concept that I'm doing right here. I just feel like this is like a slightly unnatural thing to remember. 1/2 r squared theta. Like it feels weird because there's no pi in there, except pi is encompassed by the angle that's in there right there. But that just like this feels weird to me. I don't know. I picture a circle area, pi r squared. I want to see that. So this is what the book will give you for your sector area formula. It is going to give you the exact correct answer here relative to what we did as long as you're using radians. Here our radian measure would be 2 pi thirds. I never use that formula. I always think of it as exactly how I said. Pi r squared times the proportion of a circle. So if you're in degrees, then you just do pi r squared times the number of degrees you got out of 360. Or if you're in radians, pi r squared times the number of radians you got out of 2 pi, because that's one full rotation right there. So I think it's easier to remember this formula and then to use the formula, therefore, when I think of it in these terms right here. So this is one of those things. I don't care which one you do. I care if you can compute sector areas formula for me. I just never, this isn't like a natural thing for me to think of. I think pi r squared when I think circle area, so I want pi r squared directly in my formula. And then you're just multiplying by the fraction of the circle that you have right there. So I think that this is a better way to think about this, but every one of these 4 versions on the screen right here is exactly identical, and I should say in radians. Again, just like our arc length. That one you have to be in radians for. Over here, you could just think about it either way, as long as you know that 360 degrees is also the same as 2 pi radians, right? So there's our sector area. Nothing crazy right there. Let's do one last example here. This is a book example, or I changed some numbers here from a book example. But this is a good one to kind of get like, I don't know. I feel weird not doing any real world examples, considering trigonometry is very much a real world application kind of branch of math here. So suppose we got 2 cities, A and B. And important for our computation, it needs to be the case that these 2 cities are vertical of one another, sort of the way that we orient our globe here. They're due north, south of one another. Given that city A is at a latitude of 34 degrees and city B is at a latitude of 36 degrees and 30 minutes, by the way, here's our minutes and seconds first consideration here. Find the distance between the 2 cities here. All right? So we want to kind of phrase this up in terms of some things that we have seen today. See if we can work our way through this. We got some minutes in there. We're going to have to deal with that. Nothing too crazy. So what I'm going to do is I'm going to picture a cross section of the Earth, which is a circle. I'm not going to draw a circle that small. That's not helpful. We draw a big circle, so it's all lumpy. Hey, that looks more like you should expect my circles to look like. So here is probably what the Earth looked like a couple billion years ago before it had smoothed out into more of a sphere. So the Earth is pretty close to being a sphere. It's known as an oblate spheroid because it's slightly not a sphere. It turns out that the Earth is slightly fatter at the equator because of the rotational force associated with the Earth kind of pulling out at the equator more. It's also the case for different reasons due to like how much the Earth's crust weighs versus like the oceans weighing things down, that the bottom hemisphere of the Earth is actually a little bit fatter than the top hemisphere of the Earth, but that has a little bit more to do with like plate tectonics than it does to do with like rotation of the Earth. In any event, we think of the Earth as a sphere. It's not a too terrible estimate to make right there. So what we're picturing to ourselves is we've been given these 2 latitudes, right? One latitude is at 34 degrees right here. So this is going to be the location of city A. And then the other one, just barely more than that. Okay, I couldn't draw it as close as they realistically are. Is going to be city B, right? A is at 34 degrees. So relative to this line right here, it's 34 degrees to get from the dashed line rotated to A. It's 36 degrees and 30 minutes to get from the dashed line rotated up to B right here. What we want to know is what's the distance between the 2 cities, right? So our desired quantity, the thing that we are interested in, is we want this arc length right here. So we want to go ahead and find that arc length here. So the good news is that we know our arc length formula. S equals r theta. That's my arc length formula. I want to find the arc length, the distance on the Earth between those two cities. So our driving distance, in a sense, if there was a straight road between the two. What I know that I need here is I need a radius and I need an angle in degrees. Oops, sorry. I knew that there was, I'm thinking about the units mattering, an angle in radians, right? And notice we've been given two angles measured in degrees. So first things first, I need a radius. This is information I didn't give in the problem right here, but we need to know the radius of the Earth, right? Good news about radius of the Earth is something that you can easily look up. Radius of the Earth is approximately 3,960 miles. That feels weird to me to say because most of the times I'm talking about radius of the Earth, I'm doing physics problems, and if I'm ever in physics class, I'm using metric and we're using kilometers. I think that's something like 6,000 kilometers. I'm not even going to guess it right now. I don't remember this from physics years ago. In any event, 3,960 miles is the approximate radius of the Earth right here. So that'll be a relevant measure for us. The other thing that we need is we need the difference between these two. All right, so our angle here, our angle of interest, notice that we have one angle that opens all the way to 36 degrees in 30 minutes, one that opens up to just 34 degrees. We want the difference between the two. So, because that's going to be the amount of angle that was swept out to be associated with the arc length of interest right here. So what I need is 36 degrees and 30 minutes minus 34 degrees. And it looks like that's going to leave me with 2 degrees and 30 minutes. So I actually have two conversions that I need to do right now. One, I don't like minutes at all. I want to get that into being a decimal number of degrees. Two, I actually need to be in radians, not degrees at all, but I can't convert into radians till I get decimals for my degrees right here. So remember that there are 60 degrees in, or sorry, 60 minutes equals 1 degree, right? And so therefore, 30 minutes equals 1/2 of a degree. All right, I can just divide both sides by 2 right there. So that says to me that 2 degrees and 30 minutes is really equal to 2.5 degrees. And you know this, 30 minutes is half of an hour. That means that 30 minutes is half of a degree. That's all that just happened right there, right? So 2 degrees and 30 minutes, we could just write in just degrees as 2.5 degrees. That's sort of like me, instead of saying that homework took me 3.5 hours, I could instead say that homework took me 3.5 hours. It's the exact same type of conversion that we just did right there. So it looks like this is our theta in terms of degrees. Let's convert into radians now. So hold on, let me just make some notes here. Convert minutes. And now convert to radians. Now we get 2.5 degrees times, I know I want to cancel degrees and be left with radians, so I want my degree stuff on bottom. So that means I'll do 180 degrees on bottom with pi radians on top, the two equivalent measurements. 180 degrees is pi radians. We get a cancel, cancel, and that leaves us with whatever 2.5 pi over 180 is going to be. I think I'll go ahead and get a decimal on this, but since I know I still need to do more calculation with this guy right here, I want to make sure I keep lots of decimals with this. Rounding is something that you should technically only do once at the very end of any problem. If you're going to do multiple layers of rounding throughout a problem, it matters more that you keep more decimals along the way, because otherwise you will accumulate error from your rounding with each layer of computation. So I'm going to keep like 4 decimal places on this guy right here. So 2.5 times pi divided by 180. And I'm getting 0.0436. And in fact, I'm going to keep even a few more than that. I'm seeing here 0.043633. And this is equal to our theta measurement right there, right? This is the number of radians that we have traversed if we have traversed 2.5 degrees. Those are equivalent to each other. So the good news is that we now have a radius for ourselves. We now have a number of radians for ourselves, so we can go ahead and answer the question now. Now we can come back to our S equals R theta. That should be equal to our 3960 miles times our 0.043633 radians. By the way, another thing I want to say about rounding is when you have tiny numbers like 0.043633, when you do rounding, you are taking away kind of a big chunk of the number because the number was so small to begin with. On the other hand, if this number was like 120.043633, then by rounding, you're losing only a tiny fraction of the overall value of that number. So also remember that the smaller your numbers are, the more you need to not round them. Big numbers are okay to be rounded. Small numbers, you need to keep more digits of precision in there because you don't want to change the value by a large percentage of its value by rounding. Right? So all I got to do is go to the calculator. And by the way, when I'm looking at this in my calculator, I mean, I have my, oh, I know it's flipped for you guys, but I'm sure you can sort of see what I'm seeing right there. There's my 0.0436 that's in there. It is my old value in the calculator. So I'm just going to hit times 3960, and again, I know it's flipped, but I also think that you can kind of interpret my flipped calculator right there. So really in my calculator, I'm actually keeping every decimal that my calculator gave me here, and this is going to tell me that it seems like there is 172.79 miles is the distance between these two cities if they are separated by 2.5 degrees of latitude on the globe right there. By the way, notice this is only true if these cities are vertically north-south of each other. If they weren't, then we'd also have to take into account that there is an angle difference here, like a longitude difference as well. We can do that. It just gets a little bit more complicated out there. So for the purposes of our sort of simple problem here, we wanted to be vertically oriented there. So that was the last example I wanted to do today, another little arc length problem. So this should be able to get you through all your topics in 6.1. A big but simple thing that we have to be able to do is always convert between radians and degrees. This is something that will follow you all semester. As I said before, absolutely every one of you will just straight up know that all of these are equal to each other, even without doing the conversion, by a couple weeks from now. And that's because it's not possible to accidentally memorize that just by doing the homework associated with this class here. So realize that that is absolutely an expectation that you memorize all of your angle measurements in radians. We will get more memorization things coming up next section. But again, these are things where like you don't have to like work to do the memorization. It will happen naturally. But I'm still saying like you are expected to have that straight up memorized, that these things are equivalent to each other here. So that I've gone a little bit longer than I ever hoped to go for my videos. Hour and a half here is certainly a little bit more than I'm trying to do for each video. But I'm not going to be surprised or upset with myself if it goes about this long. I certainly won't ever go longer than this guy right here. I'll break things up into more videos than that. So here's our section 6.1. As I said at the beginning of the video, next video that I will make tomorrow will be on section 6.2. In 6.2, we'll, instead of talking about circles, we'll talk about triangles. We'll define our first trigonometric functions, our sines and cosines and tangents and all that good stuff. And again, it'll be sort of in a sense, an easy section, but in another sense, like if you don't learn that stuff, then you can't do like any other section of the entire class, right? So 6.1 and 6.2 is a simple but critically important foundation for the entire rest of the semester. So make sure that this stuff you don't just cruise right past, even if it's easy for you. Stop and make sure that you are like 100% on board with this stuff. So I'm going to make our second video for 6.2 tomorrow, which will be Friday the 15th, so that these are available for you guys during week 1 of the course here. Hit me up if you got any questions. Get into your My Open Math and do your homework. Send me My Open Math questions, all that good stuff. And I will see you guys in the next video. Have a good one.